All right. Good afternoon. Hope you guys all had a nice weekend. We're going to start. We're going to cover 1.5 and 1.6. Sorry, 1.05, 1.06. But we're going to start on page 15. Okay. So I want to kind of go through this this little demonstration activity with you.
Is that the warning bell?
Huh?
Am I late or is that the warning bell?
That was the bell.
Okay. I still need to take my quiz.
Okay, we'll talk about that afterwards.
Okay.
So page 15, you guys have this little string that we're going to kind of help us with this this activity here. So on page 15, we're going to kind of discover what a radian is. We're going to kind of see that there's a we need to be able to see that conversion and that relationship between degrees and radians. But let's first start off with what we know with degrees. I think degrees make sense to us. We can use that as a baseline, and we can kind of talk about how a radian kind of plays into that relationship. So we hope you guys all have this little string, but we'll come to that in a second. When we're measuring degrees, or we're measuring angles around a circle, we always start with kind of this zero, this initial side, right? So we could call this like the 0 degree because it's our starting point, right? And as we move our way around the circle, we recognize certain degree measures that are familiar to us. Like if we go all the way out here, that's 90 degree. That's our 90-degree angle there. So I'm going to go ahead and just mark 90 degrees here. Okay. We're not going to be completely super accurate, but it's okay. We'll just kind of just so that we can kind of, just for demonstration purposes. And if we continue starting here, this is 90 degrees, and that means if we form that half circle, that's going to be 180 degrees. We recognize that degree measure. Okay, we keep going around. So starting at 0, 90, 180. 3/4 of a circle, we're going to be at 270. We'll just keep on adding 90 degrees, right? And then from 270, we keep going. A full degree measure all the way around the circle is 360 degrees, and it kind of shares the same as our initial side, but 360 is where we actually have gone through entire rotation, right? 360 being our degree measure. Okay, so we recognize those degree measures, but it kind of helps us as we are going to see a relationship between degrees and radians. Okay, now what is a radian? We'll talk about definitions in a second, but I want to kind of start us off by having this this visual as we work through. So I cut these strings here, and I kind of try to mark it out as best as I could. So if you guys can just measure, it's for the most part, it should measure from the center to the outer ring, and we can therefore call this the what of the circle. That's the radius. Okay, so it's the radius of the largest circle that is drawn for you. Okay, so now this distance could be, it could be 5 inches, could be 4 inches, okay, whatever. Well, we know that the radius is going to be different for every circle. Okay, so just for this purpose, we're going to account for this radius here. We're going to take this distance. Okay, so the nice thing about string is we can kind of fold it along the side of the circle. So this is the radius, right? This is the radius of the circle. So we're going to use the outer ring, and I want you to start at the edge of that 0 degree, and I want you to kind of form it along the path of the circle. Okay, it's not completely accurate, but okay. Everybody have that?
I don't know.
Okay, sorry. Now, this is what we call 1 radian. Okay, 1 radian is going to be the angle measure that's associated with this distance, okay, along the circle. And this is going to be 1 radian. So you guys can mark off, you know, not going to be completely accurate here, but we'll just mark this off as 1 radian. Okay, if you guys can just try to just do a dotted line here to the center of the circle. So the angle measure that is associated with that distance that we just measured is going to be 1 radian. So we can say that over here, theta is equal to 1 radian. Okay, and if we had to kind of do a rough estimate, maybe that's like around 45, 50 degrees, right? Somewhere between 0 and 90. Okay, we're going to be able to figure out a more accurate way later, but right now, just kind of eyeballing it, looks like it's somewhere between maybe 50 degrees, right? So, but eventually we're going to have a much more accurate way of working our way through. Okay, so that's 1 radian, right? Okay. Now, continue around the circle. That's 2 radians. Mark that off. So that's going to be the angles associated from, right? So I'm going to say 2 radians here. And then continue around. Looks like we're a little bit short of that 180 mark. So I'll call this 3 radians here. So 180, the relationship between 180 and radians looks like it's 3 and change, right? It's a little bit short. Does anybody know what that distance is? 0.14. Okay, so here's the relationship here. That's what pi is. Pi is that using this distance, okay, and you're measuring it around the circle, 3.14, that's what pi is. Pi is using that radius to measure around your circle. So that 180 degree is going to be equal to pi. So that is going to be how we're going to convert from degrees to radians. It's that relationship. So half a circle is 180 degrees. Half a circle is also 3 and change radians, so we call it pi radians. So pi is 3.14. And we just measured it, right? I mean, it's not accurate, completely accurate, but we know it's going to be a little bit more than 3. So that's 3.14. Okay, let's continue working our way around. So starting at the 3 radian mark, we should be able to work our way to somewhere around 6. This is my 4 radian mark. By radian. So it's a little bit short of that full circle, but this is only 6 radians. Pi is 3.14, so if I do 3.14 plus 3.14, it's like 6.28, almost 6.3. So if I fill in that gap there, that's going to be 6 radians and change. So that's going to be 2 pi. So we associate pi with half a circle. We associate a full circle with 2 pi. So whenever you see radians, you just know that that is a measure that is coming from the radius of that circle. Okay. So it doesn't matter what the radius is. We should be able to take any radius and make our way around the circle and convince ourselves that we're going to get 2 pi every time we measure our way around the circle. Okay, so I didn't have a notch for the smaller circle, but you can kind of just put your finger. So why don't we try it for the smaller circle? Measure the radius, and then see if you can convince yourself that you can make your way around the circle in with 6 radians. Okay, so this is now my radian measure here. That's 1, 2, 3, 4, 5, 6. Okay, so pi is basically that relationship between the radius and the circumference of the circle. That's what pi is. It shows that relationship between the radius and half the circumference of a circle. Okay, so I wanted to kind of do that activity first so that you have a visual idea as to how we're getting, what radian means. Okay, so now let's do a more formal definition, and let's go back to page 14. So page 14, the top of the page kind of just walks through the activity that we just did. And I'm just going to go down to the definition of radian. So definition of radian. The angle that we submitted initially was in terms of degrees. Radian is another unit that we can use to express angle measurement. More specifically, a radian is defined as the unit of measure of an angle equal to an angle at the center of a circle whose arc is equal in length to the radius. Okay, so we started with the radius and we just took that distance and we molded it to the shape of the circle, and that is how we come up with these radian measures.
Is it like A and C? Next to whose?
Whose arc? Sorry, ARC.
Oh, arc.
Okay, so anybody still need to look at this definition here or still copying it down? Okay, so here is our connection between degrees and radians. We know circumference is equal to 2 pi r. Okay. We know that 360 degrees is equivalent to 2 pi radians. And I'm going to abbreviate radians as RAD. We saw that with our circle there, how half a circle is pi and 360 is 2 pi. So algebraically, we can just divide both sides by 2, and that will take us to that relationship that we know that we're going to use this 180 degree is equal to pi radians. This is going to be how we're going to convert from degrees to radians and vice versa, from radians to degrees. So therefore, 1 radian is just going to be equal to 180 divided by pi, right? 1 radian, if I divide pi from both sides. So this is how we're going to be converting from 1 unit to the other. So if I'm starting with degrees, that means I want the degree measure to go away, and I want pi to be in my answer in terms of radians. So if I have something in terms of degrees, I'm going to multiply by pi over 180. That will ensure that I get the degree units and this 180 degree to kind of pair up and cancel out. And that will allow me to have my conversion, my units in terms of radians. And I want pi to be in my unit, so pi is going to be in the numerator. Okay. Likewise, if I want to convert from radians to degrees, now I'm going to be starting with something that has pi in it. I want that pi to go away, so I need that conversion to have pi in the denominator and degrees in the numerator. Sorry, let me write that better here. 180 over pi. So it's kind of like this dimensional analysis where we're kind of matching and pairing the units that we want to disappear and the units that we want to keep. Okay, next page. Oh, sorry, page 16. Okay, let me just read through this page here. An angle is formed by two rays. Okay, angle is formed by two rays. We see that we got a ray here and a ray here that share a fixed point, endpoint, known as the vertex. So that's the vertex of my angle. One of the rays is fixed to form the initial side, so kind of the positive x-axis as our initial side. That's the side that we start with. And then we're going to rotate that to form an angle until we reach our terminal side. Our terminal side is our ending side. And the angle that is formed is what sits between, right? Theta. An angle with its vertex at the origin and the initial side along the positive x-axis is an angle that is in standard position. Okay, so we call this a standard position. Typically, whenever we create an angle, we go counterclockwise to do positive degree measures or positive angle measures. But if we rotate in the clockwise direction, right, going backwards here, clockwise direction, that's going to form our angle in the negative direction. So if this goes 30 degrees clockwise, then we say that this is negative 30 degrees. Okay, so I think the rest of this page is a review. I'll just read through it. Know the quadrants and the signs for x and y in each quadrant. We know anything in the first quadrant. If you imagine any order pair here, your x and y value are both positive. If you can imagine a point that lives in the second quadrant, any order pair here has a negative x value and a positive y value. Anything in the third quadrant, any order pair in the third quadrant, you expect that order pair to have a negative x value and a negative y value. And then fourth quadrant, you expect a positive x value and a negative y value. If the terminal side, if the ending side of an angle falls on one of the axes, the angle is a quadrant angle. There are 4 quadrant angles in a unit circle. They are 0, parentheses 360. 90 degrees is on the y-axis, 180 degrees is on the negative x-axis, 270 is on the negative y-axis. Okay, more vocabulary that you guys know. Right angle forms 90 degrees. Acute angle is less than 90 or between 0 and 90. Obtuse is between greater than 90 and less than 180. I'm sorry. Yeah, less than 180. Okay. Complementary angle, 2 angles whose sum adds up to be 90. And then supplementary angle, 2 angles whose sum adds up to be 180 degrees. Okay. Okay. Next page, page 17. We've discovered a lot of this from the previous pages, but just going to kind of review again. Again, the new unit of measure for angles that we discovered is called the radian. And it's the measure of an angle in a circle whose intercepted arc. So we call this an intercepted arc because it's the arc that's associated with this angle, right? If I take the ray of this of the sides and wherever it intersects the circle, that's the intercepted arc. Okay. We know that's going to be this 1 radian is related to the length of your radius. Okay. Remember the formula relating the length of a radius of a circle to the circumference of a circle is c equals 2 pi r. Okay. So we're going to practice converting from one unit to another. So we'll start here. If I want to convert from degrees to radians, I want the degrees to go away. So that means I want the 180 to be in the denominator. I want my unit to be in terms of radians. So that means I want pi to be showing up in my final notation. So pi is going to be in the numerator. So if I want to convert 120 degrees, I'm going to have to multiply by pi over 180 because I want pi to show up for radians and I want the degrees to cancel out. And we know that pi and 180 are equivalent because we discovered that as we worked our way around our circle. So you can either put this as one fraction, you can cancel out between numerator and denominator. We know that 120 and 180 can both be divided by 60. So that's going to reduce to 2 over 3. We keep pi in our answer. And then our abbreviation for radians is RAD. So 120 degrees is equivalent to 2 pi over 3 radians. Okay. Likewise, if I'm starting with radians, that means I have something that has pi in the numerator. And if I want to get that to be in terms of degrees, I don't want pi to be in my final degree measure. So that means I want pi in the denominator, which will allow it to cancel out nicely. So that means I know I got to go through, I want to do 180 over pi and not pi over 180. Okay, so whenever you convert, you always have to decide which order is 180 and pi going to be. Okay. So I know pi is to be in the denominator for the pi's to cancel out, which means 180 will be in the numerator. Get the pi's to go away. And the rest we can use our calculator or we can reduce by hand. 180 divided by 6 is 30. 30 times 5 is 150. Okay, any questions? Okay, so this should be quick. You guys can go through 10 through 17. If you start with degrees, you know you got to multiply by pi over 180. If you start with radians, you know you got to multiply by 180 over pi. And then in your answer, make sure you provide the notation. If it's radians, then put RAD. If it's degrees, make sure you have that degree symbol. So take a couple minutes to finish those. I'll walk around and we can check our answer. Feel free to use your calculator.
Okay.
Okay, so check your answers when you get a chance. Are there any ones you want me to go over with you, or yes? Number 15? Okay, So 5 pi over 2, I want to convert that to degrees. I know that pi's cancel out. That's a good sign. I know that I have my conversion rate in the correct order. And I'm just going to simplify here. I can multiply across and then divide by 2, or I can just see that 2 and 180 can cancel out nicely. And I'm just left with 5 and 90, which multiplies to be 450.
Is it okay if it's more than 360 degrees?
Yes, but you know what? You're right. We could subtract 360 to get something that's a little more recognizable. But let me talk about that later. Okay, so for right now, we'll just kind of leave it as whatever they give us. But we are going to talk about how to get something that has rotated, certain times around the circle down to something that we recognize between 0 and 360. Okay. But to answer your question, you could also say this is 90 degrees, and that'll be fine as well. Okay. But okay. But we will talk about angles that fall outside of 0 and 360 in more detail later. Okay, good. Any other questions? Okay. Okay, so I want to start the next section here. This is on arc length notes. So 1.07, this is page 18. Everybody good with this page? Okay. Good. Okay.
Oh, we just did the homework.
Right. We did the homework. So I'll just check this tomorrow at the beginning of class. But we're kind of going ahead. The reason why is because the further ahead we can get, the more time we'll have for review. So if we can finish all of our notes by Wednesday, then we can have Thursday as review day for our quiz. Okay. So, but yeah, you're right. If you did that, then you've already completed your homework. Everything else is going to be for the following day. Okay, just as review, can you just try A and B real quick? Before we move on to our topic with arc length.
Just the end.
Yeah, just A and B. Okay, so hopefully you guys had a chance to work on them. Check your answer when you're done. And then we'll go ahead and copy the notes for this. Make sure you have your units in place. Make sure you're multiplying by the correct conversion rate. Any questions with A or B? All right, copy down the notes here, and I'll go over arc length in detail. I'm going to read the notes here. If theta is the measure in radians of a central angle, so central angle is just an angle formed from the center of the circle with the radius r, so that's just going to be that length there. Then s, we assign the length of the arc to be a variable s, intercepted by theta, so that just means it's the angle associated, sorry, the arc length associated with this angle measure. And the formula is, if I want to look for the arc length related to the angle with a given radius, then the formula is S equals R theta. Okay. So arc length is represented by S. A lot of times we have to understand, okay, arc length and radius will share the same units. Okay, let me put that here. So arc length is not going to be a degree or a radian measure. Arc length is basically, imagine taking a string and kind of following it along the path of that arc, and then taking that length, straightening it out, and then measuring it against a ruler, and then asking what that length is. Okay. So your arc length and radius will always share the same units. Now, the potential tricky thing is knowing what to do with that angle measure that they give you. If the angle measure that they give you is in terms of radians, then that's great. You can just plug in the formula. There's no adjustments needed. It'll just go directly into the formula and you just solve for whatever variable the problem is asking for. Okay. But if the problem gives you theta being a degree measure, then we got to do some conversion because this formula is meant for radians. Okay. So if something is a degree measure, you have to convert it to radians first before you can use this formula. Okay. So if something is like 60 degrees, I got to convert it to, in terms of pi, in terms of radians, before I can use this formula. So we're going to start off with easier ones where we don't have to do that conversion, and then we'll practice with the ones where you do have to convert first before using the formula. Okay, everybody good with writing down these notes? All right, let's look at example 1. Okay, example 1, I'll put the formula here. S equals R. Example 1, find the arc length if the radius is 8 centimeters and the central angle measures 3 pi over 4 radians. We know that there's 3 variables involved here. Some are given, one is unknown. So I'm just going to go ahead and list them out and see what we can fill in, see what we know, see what we don't know. Okay, find the arc length. So we're looking for arc length. Arc length is associated with variable S. So that's the unknown in our problem, question mark. If the radius is 8 centimeters, that's R. And the central angle measures 3 pi over 4 radians. Okay, that's a good sign. That makes it easier for us. We don't have to do any conversions. It's already in terms of radians. We know that value is good to go. Now we can dump everything into our S equals R theta formula and solve for S. I'm going to, for now, just going to convert it to a decimal value. So 6 pi. I'll round it to 3 decimal places. So it's basically 6 times 3.14. So that's around 18. Use our calculators, though. Make sure that you don't assign S to be a degree or a radian, but rather you want to make sure that your arc length has the same units as your radius. Okay, it's something you can measure against a ruler. Okay.
Do you have to turn it to decimal?
I think for now, I want us to move it to a decimal because I just want to enforce the idea that it is not a measure. I think sometimes when we see that pi, it can kind of throw us off. So until we get used to it, I'm going to have you guys put it in decimal form. Okay, try number 2. Same process, same setup. If you get done with 2, then try 3 and 4 and see if you can recognize what additional step is required for 3 and 4. Okay, but I'll put 2 up in a second. All right, let's check number 2. Again, nice thing here is there's no need for us to do any conversion. We can rely on 5 pi over 6 to plug directly into our formula. And again, our units is not radians or degrees. It's the same as your radius. It's an arc length, centimeters as well. Okay, questions of 2. Okay, number 3, find the arc length if the radius is 2.5 miles and the central angle measures 300 degrees. Okay. What's different about this problem? Yeah, so we're not ready for the formula yet, right? That 300 degrees needs to be adjusted in the proper form before we can do S equals R theta. So make sure you multiply that 300 by pi over 180, get it in terms of radians, and then you can use S equals R theta. Okay. So try 3. You're going to see that same same process pop up for example 4 as well. You're able to get through 3 and 4 without much trouble. See if you can make some progress on page 19. And also you're essentially chipping away at the homework for that's due Wednesday. So we're using the same formula every time, right? We may have to do that additional step of changing our degrees to be in terms of radians. But another thing to keep in mind is that it doesn't mean that every problem we're going to solve for s. Okay, sometimes you may be solving for theta, sometimes you may be solving for radius. So I think, but the first page here looks like we're pretty much just solving for s all the way through. Okay, but we're going to see some variations on the homework page on page 19. Okay, so here's example 3.
You have to have the units.
Yes, yeah, I want us to have the units. I want you to do decimal with the units so you can kind of train your mind to know that arc length is really a measurement that you can find on the ruler, or it's not a degree or radian measure. It's taking a curved region and then straightening it out and figuring out the length of that adjusted curved region. Okay. Example 4, conversion is also necessary, but you're going to see that the angle is really large. But if you go through the formula, you're going to get your theta measure to be rather large, but that's just because we're having to kind of go around the circle multiple times, right? So that's going to increase the measure of our arc length. Okay, try example 4. If you get done with 4, we're going to see if we can at least get through 1 and 2 on page 19. Because 2, we're going to see that we may not always have, we may not always be solving for the same variable every time. Any questions with 3? Try number 4. Okay, any questions with 4?
I got 92. Not 90.
Okay. Did you get theta to be 46.513?
I got 53, or 533 pi divided by 18.
Yeah, try again. I'm getting 46.513. So if your decimal is off, then the number is going to be different from mine. Yes. Why is it not 180 over pi?
Yeah.
The reason why is because we're starting with degrees. So that means I want degrees to be above each other. Because I want my theta to be in terms of radians. Because if I want to use this S equals R theta, that theta has to be in terms of radians. Right. So if I have degrees to start with, I need degrees below to cancel those units out.
Yeah.
Does that make sense?
I like this one. I don't get a decimal, I get a fraction.
Okay, you can always convert that fraction to a decimal. Right? Here's that button.
Oh.
So 2665 is degrees, right? I'll write the words here, degrees. If I want that degrees to disappear, I need degrees below. And that will ensure that my resulting unit is going to be radians. Okay. If it's the other way around, I can't have degrees and degrees above because then I'm getting degrees squared over radians, and that's not quite right. Does that make sense? Okay, so